Have you ever just stopped and thought about the absolute powerhouse running inside your skull? I mean, it does things that make the world's biggest supercomputers just sweat. And it does it all with this incredible efficiency. So what if, just what if, we could build an AI that actually learns from that natural masterpiece? Well, that's exactly what we're diving into.
So, get this. Your brain, right now, as you're listening to me and processing all this, is only using about 20 watts of power. 20. That's less juice than a dim light bulb. It is an absolutely unbelievable feat of engineering by Mother Nature.
Okay, now let's flip the coin. Look at the massive AI models we use every single day. We're not talking watts here, we're talking megawatts. That's enough energy to power thousands of homes just to train one model. You see the problem, right? This huge, staggering energy gap is one of the biggest challenges in AI today.
So it makes sense, doesn't it? If you want to build a smarter, more sustainable AI, where do you look? You look at the best blueprint we have, the human brain. And this idea has kicked off what many are calling the third generation of AI. These are spiking neural networks, or SNNs for short, and they're designed from the ground up to mimic how our own neurons talk to each other. So how on earth does the brain pull this off? It's not magic, it's just a set of really smart design principles. First off, it's event-driven. A fancy way of saying neurons only fire when they actually have something important to say. No wasted energy. It's also sparse, meaning only a tiny fraction of your neurons are active at any given moment. And here's a huge one. Information isn't just about how many neurons fire, but precisely when they fire. The timing is everything. And the whole thing is held in this perfect, delicate balance between go signals and stop signals.
Okay, this all sounds amazing, right? But there's always a but. There's a catch that has really held this whole field back for years. While these spiking neural networks promised to be just like the brain, to get them to actually perform well on difficult tasks, researchers often had to strip away the very biological features that made them so special in the first place.
And that created this really frustrating trade-off. If you wanted high performance, you had to basically ignore the precise timing of the spikes. You had to throw out that crucial balance of go and stop signals. It felt like you had a choice. You could have a fast AI, or you could have a brain-like AI, but you couldn't have both.
And that brings us to the big, central question that's driving this brand new research. Is it even possible to break that compromise? Can we finally build an AI that's both super high-performing and stays true to its biological roots?
Well, it turns out the answer might just be a resounding yes. Enter a new kind of architecture, the CSTM Enhanced Spiking Neural Network. This thing is designed to solve that exact dilemma. It's an AI that's trying to get its high performance because of its brain-like features, not by getting rid of them.
So how does it do it? Well, instead of just taking one look at the data and spitting out an answer, this network thinks a bit more like we do. First, it takes a quick glance at the information. Then it goes into what's called a thinking loop. It actually refines its understanding over and over again, kind of like how you'd mull over a tricky problem, right? Only after it's done that refinement does it make its final call.
And here's the kicker. This model doesn't cheat. It keeps that vital 80-20 balance of go and stop neurons, the exact ratio that's so fundamental to how our own cortex is wired. But that iterative thinking, that's really only half the story. The second massive innovation is how this network actually listens to its neurons. It's not just counting how many times a neuron fires anymore. No, it's decoding the rich, complex language of time that's hidden in the rhythm of those spikes.
And to do this, it pulls out 4 key features from the timing. First up is something called the temporal center of mass. Basically, this just asks a simple question. On average, when does this neuron like to fire? Is it an early bird that reacts instantly, or does it prefer to chime in a little later in the conversation?
Next, you've got temporal variance. This is all about consistency. Does a neuron fire with absolute pinpoint precision every single time, or is its timing a little more random? This tells the network how reliable and consistent that neuron's signal really is. Third, it's on the lookout for burst patterns. Now you can think of this like a neuron shouting to make sure it's heard. A burst is a super rapid-fire sequence of spikes, and it carries a much stronger signal, so the network keeps an eye on which neurons are using these bursts to really emphasize their point. And finally, we have the early/late preference ratio. This really helps the network figure out what a neuron's job is. Is it a first responder that jumps on the initial signal? Or is it part of the cleanup crew, involved in the final stages of putting the puzzle together? Okay, so let's recap. We've got an AI that thinks in loops and actually understands the language of time. It's all very cool, but here's the million-dollar question. Does all this brain mimicry actually work? Does it really make the AI better? And the answer is a huge, resounding yes. When they put it to the test on a classic handwriting recognition task, the CTM-SNN scored an incredible 98.10% accuracy. That firmly puts it in the big leagues as a top-tier, high-performance model.
But honestly, that number is even more amazing when you add some context. Yeah, you can see other models here that might edge it out by a tiny fraction of a percent, but look closer. The CTM-SNN is the only one at the top that gets that score while sticking to the brain's rules, maintaining the EI balance and analyzing those complex timing patterns. It got the performance without the compromise.
In fact, what the researchers found was totally counterintuitive. They realized these biological features weren't a handicap they had to work around, they were the very source of the model's strength. This quote from their paper says it all. It was the brain-like constraints and the iterative reasoning that gave them the biggest boosts in performance.
And, just look at what happens when you start taking these pieces away. You take out that thinking loop, boom, accuracy plummets down to 94%. You mess with that proper brain-like balance of neurons, it drops again. This is the smoking gun, the proof that the biological realism isn't just for show. It's what makes the whole thing so darn smart.
So, why should you care about all this?
Well, this could be the future of AI. We're talking about powerful AI that can run efficiently right there on your phone or in a tiny smart sensor without needing to constantly call home to some massive data center. This means the potential for huge energy savings, making AI sustainable. And it opens up brand new doors for things like smarter robotics and real-time video analysis that just weren't practical before. When you step back, this research really suggests that the next big leap in AI might not be about brute force and more power, but about smarter power. It leaves us with this really fascinating question to chew on. What could we truly achieve if our artificial intelligence finally became as elegant and as efficient as our own?